It's up to the author to include what to be there or what not to be there. But there are many things which may be missing in the that notes. Notes is only a sort of guide rather than the full requirement of the topic, full requirement of the knowledge of the topic. Okay. So today I am slightly changing the uh, notes from this notes, and then I am changing it to a book by Professor Limay, very popular book in India. And I thought, let me give you a few things from that book, what we have missed here. So let me start with Lemay's book today. Before I start, I'll send you the whatever the material I have used for the whatever this video talk. I'll send it to you by PDF.
Okay, sir.
Before I start, Sonam Kumari, do you have any difficulties?
No, sir.
Sri Lanka, Sri Siri, do you have any difficulty? Pragya Tipati, do you have any problems?
No, sir.
Okay. Dhanush Reddy, do you have?
Sir, while you are teaching, can you please most of the time use board instead of reading the PDF?
Most of the time?
Can you use notepad to write instead of reading PDF most of the time? Please use board.
But many times I use it only when it is necessary. No, the problem with using the writing pad is that I have to switch from uh, one sharing to another sharing. Sometimes it takes time. It doesn't matter. I will use it. Yeah, sure. Any other thing?
No, sir. Thank you. BT23MA001. Zomu. You have anything to ask?
No, sir.
No? Okay. B23M005. I don't know who it is. No problem. All right. Most likely I will be there on 31st evening this month at NIT Mizoram. So if you have any difficulties, you can ask me there. Okay. I'll try to push in the notepad. Okay.
Okay, sir.
This notepad is not switching on. I don't know why. I'm trying to connect the notepad. Okay. There's no light in that. Okay. Just 1 minute. Huh? I'm trying to open the notepad. Somehow it is not opening. Okay.
Okay, sir. No issue. We will
Only today
waiting.
I will check up. There may be some problem with the drivers.
Okay.
I'm sharing the screen. Just 1 minute. Huh? Google is little slow today. One minute. Huh? This is the. Let me. So I'm trying to give you what we have missed from the other books. Okay. So for one less than or equal to p less than infinity, the set LP is the set of all equivalence class of p integrable functions. See, this is what we had equivalence class. The reason is that if f equal to g, then this almost everywhere or almost surely, then f and g are considered to be almost the same. You don't make a distinction. So what you do is you take all integrable functions and use this equivalent relation. F equal to g equal only if f is equal to g, almost everywhere, almost surely. That is an equivalent relation. And that will partition the LP spaces into these integrable features into disjoint classes. Those disjoint classes are called LPE functions. So that is what is to be understood, which is not given in the notes which I have sent to you. So LPE is the equivalent class of functions, and what we are trying to say is that you look at all those integrable functions for which the mod of x raised to p is finite, integral. Whatever this measure is, it's some good measure. we use usually on Rn or R. This P is called the index. P equal to 1, it is L1E is a state, and norm 1 is clearly is the norm on it. That's an obvious effect. If P is greater than 1, then you have to use the Minkowski's inequality. Okay, that we have done it up here. What is that Minkowski's inequality? Norm of x plus y raised to p is bounded by norm of xp plus norm of yp. If you don't know the proof, I will send the notes for it. Okay. Hence, this LPE is a linear space, and this norm P is a norm on that. Now you consider two numbers, one less than or equal to P, less than R, less than infinity. Please note this R has nothing to do with P except that it is greater than P. The conjugate of P is always denoted by P prime. Okay, don't get mixed up with these two. Let's assume the measure of P is finite. Then you can show that norm of x raised to P is nothing but the norm of x raised to R into measure of E, this one. How do you get this one? This you get by Holder's inequality. Okay. So if R by P is greater than 1, we can find Q such that, etc., etc. That's the proof given here. More or less, the Holder's inequality is what is used. Okay. Now, when P is infinity, you denote this space as L infinity. What is this L infinity? Set of all equivalent classes of essentially bounded functions. I will explain to you more on this when I come there. For x belonging to L infinity, you define the norm to be essential supremum of mod x. No issues. These functions x are all mapped from E to R, E to K. Either K is real or complex. Okay. It's easy to show that this norm of x plus y infinity. This is obvious because you take xt plus yt, that is less than or equal to norm mod xt plus mod yt. You replace this by infinity. Then you take the essential supremum on the left. You get this one. So it also becomes a linear space. That's obvious. So if m of E is finite, okay, and x is in L infinity, you use this integral, okay. Norm of xp is the integral of E mod x raised to p dm raised to 1 by p. Now, if this mod x is finite, then mod x raised to p is also finite. So you remove the bound from the integral, but then you cannot have equality. It will be less than or equal to. So there is a power p here. There is a 1 over power p here. So that will give you the. And you have to take here the measure of. Where is that? Okay. So you're taking p minus r is greater than p. So what you do is you take r minus pr over pr. That's the measure of that into x raised to r. So write this mod x raised to p as mod x raised to r into mod x raised to p minus r. R minus pr, whatever it is. Okay. This is what you have here. Okay. So if r by p is greater than 1 and q is greater than 1, then by Holder's inequality, you have this one. So this is what was missing in that notes which I wanted to give you here. Okay. The second issue is this is a simple matter that when you have this in this integral, you remove this mod x by its essential supremum. So what you get is here the L infinity norm of x. What remains in the integral? Now we have pulled out this mod x raised to p. What remains is 1. When you integrate 1 with respect to some measure on E, then you get the measure of E. Okay. But there is a raised to power 1 by p. So what you have here is that where is that? Yeah. You get the measure of E raised to 1 by p into the norm of this. This is finite. This is finite because the measure of E is assumed to be finite. E is a bounded measurable set, essential. Okay. So this is the story that we have. So what happens if E is not finite, etc.? Measure is not a bounded set. Second thing is if xn goes to x in L infinity, then xn goes to x in LPE. So how do you get this? You have to use what is called dominated convergence theorem. Okay. I will come and do it in your place. Okay. All right. The comment which I was making is that this what happens if measure of E is infinity? That is, E is not a bounded measurable set. Then there may not be any relation between the LP spaces. Okay. So the example given here is for E equal to R, real line. And the measure of R is infinite. Okay. So it's not a bounded set. Now you consider x1t equal to 1 over root t if 0 is less than mod t less than 1. Okay. Actually, it's an example on interval 0, 1, but he has extended to R by taking the x1 t to be 0 outside this interval. So this function lives in the interval 0 to 1. All right. Take x2t equal to 0 if mod t is less than 1 and equal to 1 by t otherwise. Both these functions are measurable. Okay. This x1 belongs to L1R. That's obvious. Okay. But you have to integrate this function. Outside the interval 0, 1, it is 0. So it lives on. So you have to integrate 0 to 1, 1 over root mod t. But mod t is t because t is positive in 0 to 1. 1 over root t integral is root t, right? d by dt of root t is 1 over root t. So you will get 2 by root t. So integral of this one will be twice root t. And between 0 and 1, it is finite. At 0, it is 0. At 1, it is 1. So you get a 2 or a half or whatever it is. So this function is L1. But it does not belong to L2R. Why? When you take, for x1 to belong to L2R, you have to take mod xt, square it, t is 2. When you square this one, what you get is 1 over t. Square root disappears. But 1 over t will be log t when you integrate. So integral of 1 over t will be log t, but at 0, it gets unbounded. Okay. The value of log at 0, that is log x, as x goes to 0 is minus infinity. So therefore, this integral will not exist. All right. So this is not in L2. So this function belongs to L1R, but it does not belong to L2R. That's not the case, when you are looking at the finite measure. So when the measure is infinite, you get into such problems. It does not belong to L2R or it does not belong to L infinity also, because the essential supremum of this function is infinity. 1 over root mod t as t goes to 0 will be infinity. Therefore, essential supremum will be infinity. So it is not in L infinity also. Now, while this function x2t equal to 0 equal to mod t, etc., belongs to L2R because you take integral this, there is no issue with the 0 to 1. You square it up. When you square it up, you get integral of 1 over t squared. And the integral of 1 over t squared is 1 over t. At t equal to 1, it is 1. at t equal to infinity, it is 0. So that integral will be 1. So it will belong to L2. But it does not belong to L1 because when you integrate 1 over t, okay, you get actually log t. And log t will be infinite. All right. So that's the point here. You have to be slightly careful here, okay, with this. I will modify this example slightly. Okay. It is better to take from 0 to infinity rather than on the path. That's what I mean. Because when you want to integrate this 1 over t from minus infinity to 1 and 1 to infinity, you will have some problems. That's why I'm saying. I will explain to you when I'm here. Now we have what are called function spaces. Let T be any set and BTB denote the set of arcs now scalar valued functions. Scalar valued functions meet either the value is a complex number or a real number. Okay. We take all the bounded functions and you define norm infinity. This I have done it yesterday. Done it on 301. Anyway, that matches infinity. So you have three sets here: CT, C0T, and CCT. And this, I don't know, there is no compactness. Okay. So you should know the support of a function. All right. I will not to do it. Okay. If you don't know, I'll let you know. So a CT is the set of all continuous functionality. C0T is the set of all components for which for every epsilon 0 there is a compact set E such that E is contained in T and norm of xt is less than epsilon. If T is not in T. That's the C0T. CCT is the function which
Sir,
yeah.
sir, can you elaborate C0T again, sir?
C0T
Yes, sir.
essentially means the function is 0 at the boundary.
Function 0 at the boundary point.
Okay.
Okay, sir.
This tablet is
Uh,
not working, otherwise I would have written on that.
okay,
So
sir. Okay, sir.
what essentially it means is that when do you say that some function is 0 at the boundary point? For any epsilon greater than 0, if you take a neighborhood of the boundary, it should be smaller than that. That is
Okay,
what
sir.
is written here. Okay. What I
Okay,
said is
sir.
you can take this in a different way that x belongs to CT such that the boundary value of x is 0. This 0 simply says the function is vanishing at the boundary. What CCT says is outside a compact set in T, it is 0. There is a compact set E in T such that outside this T, okay, outside this compact set, this set E is compact, okay. Outside this compact set means what? T is not in E, xt is 0. So obviously, when you take some set in T and you compact set, it has to be strictly contained in T. So when you take the complement, it will obviously contain the boundary. Okay. So this is a larger space. C0T is a smaller space because there are functions which need not vanish on the. Suppose you take T equal to the open closed interval 0, 1. Take x equal to xt equal to 1. It is continuous function, but it doesn't vanish. But if you take functions like t into 1 minus t, then it will be in C0T. It's continuous, it vanishes at 0, it vanishes at 1 also. Something that you have used this part of thing when you do interpolation. Now, if you are given a function and you want this function, you know the value of the function at some points, you want to construct a polynomial with these values, which is called the polynomial approximation or the interpolation. You use this sort of concept. This t into 1 minus t like that. Okay. TCP
Okay,
is
sir.
that there is a hump and then it is 0 outside the hump.
Okay, sir.
I will write some figures and then let you know on 31st or first. First, we'll meet on first.
Okay, sir. Okay, sir. Okay.
UKT is a compact metric space. I don't know.
Sir, this is another book, na?
This is MAS book.
Yeah.
I told you in the
Okay,
beginning
sir.
the book because these things are not available in that notes. But I don't
Okay,
want
sir.
to bring
Sir.
it. I'll send you the copy.
Okay, okay, sir.
I'll send a
Okay.
copy of
Thank you.
whatever I have done today. PDF copy. Sure. By evening or tomorrow
Okay, sir.
morning, I'll send it. Sure.
Okay, sir. Okay, sir. Thank you, sir.
So in case T is a compact metric space, those who have studied compact metric space, then we can show that these three are same. There is nothing great about it. Let T be equal to 1, 2, 3 union infinity. Till now we never said anything on T. Now when T is 1, 2, 3 infinity, essentially what it says is that we are looking at discrete points 1, 2, 3. Okay. So this is this measure, on this T dm is actually you write d of n comma n, the distance between n and l, to be the modulus of 1 minus 1 by n. That's what you are writing. How do you define t n comma infinity? Because infinity is here, you write it as 1 by n. It is also d of infinity n. Define the distance between infinity and infinity 0. See, this is a very technical matter. Okay. So the metric, the d is a metric on t, and t is compact. I will not prove it. Okay. So now you can show all these things. Okay. So this CT can be identified with L infinity space. That's what it is. All right. Let us see. Let's not worry. Let us look at a concrete example. Let's take t equal to closed interval AB. And for k equal to 1, 2, 3 n, define Ck of AB, extend CAB such that kth derivative of x is continuous. Ck means set of all functions whose derivatives up to order k and the function itself is continuous. That is, so this k denotes the order of the derivative. Okay. So whatever the order of derivative you take, as long as it's less than k, that function has to be continuous. And for x in this Ck, we define norm x equal to infinity norm of x, first derivative infinity norm. That is the sum of the infinity norms of x, the derivative of x, second derivative of x, and kth derivative of x. Now all these things are finite because this interval AB is finite. We have taken AB to be finite. And these functions are continuous. Any continuous function on a compact set is bounded. Therefore, all these infinity norms will exist. Therefore, this x will belong to CA. You can show it's an RM also. That's simple. Okay. Inner product spaces, I will. Okay. We'll introduce the concept of the inner product. Is doing it right here. It is similar to the dot product on R2 or R3. The familiar dot product. Okay. So if you take two vectors x and y, then x dot y is summation x1 y1 plus x2 y2 in R2. And if you take x dot x, then you get mod x square. And you take the square root of that, you get the length of it. So if you have a linear inner product, so you can define this norm x equal to inner product of x comma x raised to half. So if you have an inner product, you can define a norm. And then you can have the regular. Now, this is the theorem which I have been talking to you, which was missing in that notes. Let Y be a subspace of a norm space X. Then Y and its closure are also non-linear spaces with adjust norm. That's an obvious fact. Let Y be a closed subspace for X plus Y. For X plus Y, the quotient space X divided X slash Y, you define the norm to be this triple norm. Okay, this is a definition. All right. Then this triple norm is a norm on the space X. Have you studied quotient spaces in the metric spaces? Linear algebra, did you study quotient spaces? Yes or no? Rishabh, have you studied quotient spaces?
Sir, I think we have studied, but this time I forget, sir.
Okay, all right. I will come and do it here.
Okay, sir.
Sorry, forgetting it here, I will come and do it here. Okay.
Okay, thank you, sir.
Now, suppose you have m non-linear spaces, say x1, x2, xn, and suppose each of these non-linear spaces xj has an arm. Now you look at the Cartesian product of this x1, x2, xn.
Sir, we have studied in abstract algebra, sir, quotient space.
That's a quotient group, no?
Yes, sir. Quotient group. R by yes, sir.
But what happens
This,
in the case of vector space is you have to show that it's a vector space. The same concept is continued. Okay? You define a coset, etc., right? This express
yes, sir. Coset, left coset.
express y is a coset of x.
Which are below x.
All right? Then you are using it as a group. So you look at this y as a group with plus. Then this is nothing but the coset. If you have a coset x plus y for x in x, we want to define a norm on that. So this x plus y is an element of this quotient group x by whatever y. How do you define a norm? Norm of this is infimum of x plus y such that y is in y. Okay. This is the norm on the coset of this quotient space. Question is that when you define this one, you have to show it's a norm also. You cannot simply define something and then say, oh, we are done with it. Huh? That's what I'm saying. This quotient group is a quotient of a non-linear space is very important, and let me recall to you from your group theory, abstract algebra. If you have a group G and you have a group H, is it possible to define the quotient G over H, subgroup H? Can you define G over H?
Yes, sir. If H is a sub, F is
unless H is a normal subgroup, you can't do it.
yes, sir. A condition. There is a condition, sir. Otherwise, we cannot.
H has to be a normal subgroup. The same way, if you want to define the quotient in the non-linear space, this Y has to be closed subspace. It cannot be any subspace.
Okay, sir.
Just like you cannot have any group, but you have to have a normal subgroup. Here you have a closed subspace. If you are interested, I will do this when I come here. Okay. Now, many people don't do it in the. I mean, it's a long proof. Okay. Not a simple proof. So I will omit it for a while, but it's not a difficult proof. It's a long proof. This is an obvious affair. Okay. Nothing great about that. Now, the classical Heine-Borel theorem. What is the Heine-Borel theorem? Heine-Borel theorem says that if you take a closed bounded set, it has a limit point. When do you say a metric space has a Heine-Borel theorem? That every closed bounded set has a limit point. Essentially, what it says is every bounded sequence will have a convergent sequence. All right? And yeah, it's an important aspect you have to know that it's not necessarily, that not necessarily that a bounded sequence should have a convergent subsequence. I will explain to you. Unfortunately, I don't have the Wacom board working.
Sir, can you just give the examples of this statement, like how?
I'm giving you now.
Okay, sir.
So you take this L1, okay, small L1, and take the standard basis E1. E1 is 1, 0, 0, 0. E2 is 0, 1, 0, 0, dot, dot. En is nth component is 1, otherwise 0. So if you take the distance between E1 and E2, what is the distance between E1 and E2? It's the norm of E1 minus E2 or E1 plus E2, whatever it is. It will be 2, right?
Yes, sir.
If you take an element in L1, say A1, A2, An, then the L1 norm is mod A1 plus mod A2 plus mod A3. When you take E1 minus E2, what you have is 1 in the first place, 1 in the second place, 0 everywhere else. So the distance
Yes.
is 1 plus
Yes.
2. Now, when you take En minus Em, that length also will be 2. At the nth place it is 1, at the nth place it is 1. So distance between
Yes, sir. Yes.
En and M is 2. For any N and M, can such a sequence be Cauchy? For a sequence to be Cauchy, An minus Am has to go to 0 as Nm goes to infinity, right? The sequence is called Cauchy if An norm An minus Am goes to 0 as Nm. But here, this sequence En, the distance between En and Em is always 2, fixed to be 2. So it can't go to 0. That means this sequence is not Cauchy. If this sequence is not Cauchy, it is not convergent. Why? In a metric space, a convergent sequence is always Cauchy. This you might have studied, right? Not studied,
Yes, sir.
it's not a big thing. Okay. Every convergent sequence has to be Cauchy. So if a sequence is not Cauchy, then it cannot converge. Now, if you take any subsequence of this En, the distance between any 2 points is always 2. Therefore, this sequence, no subsequence is Cauchy. This En, the norm is 1. So it's a bounded set. The bounded set bounded by 1. It's a bounded set, but it has no convergent subsequence. So Bolzano-Weierstrass property may not hold in infinite dimensional space. Finite dimensional space, yes, true. Shall I explain again? Should I explain?
No, sir.
See, the sequence En, the distance is always 2 between 2 elements. Therefore, no subsequence can be Cauchy. If no subsequence can be Cauchy, no subsequence can converge. But it's a bounded sequence, so it has no convergent subsequence. So Bolzano-Weierstrass property is not true in L1. Same example you can use it for LP also. Do it yourself. Only thing is that norm will be instead of 2, you will get a root 2 for 2, and then it will be 2 raised to 1 by p for LP. Anyway, the root 2 raised to 1 by p is a fixed number. It will never go to 0 as n goes to infinity. So these are all sequences in LP spaces. This is what is called the standard basis. This will not have a convergent subsequence. See, this is the first departure of what we have studied in finite dimension. and what we are studying now in infinite. Okay. So Bolzano-Weierstrass property is no more true for infinite dimensional spaces. So naturally the question is, when is it true? For compact metric spaces, it is true. I'm not sure whether compact metric spaces is done or not, but I'll come and give you a quick. I'll be there on first, second, third, 3 days. Okay. So whatever doubts you have, can get it clear. Whatever more information you want, you can get it clear. Okay. So that is the
Okay, sir.
first part. Now let me also tell you, every closed bounded set in Rn is compact. Do you know compactness or not?
Yes, sir. We have studied compact sets, sir.
Compact.
Uh,
In
linear
Rn,
universe.
yeah, in Rn, every bounded closed set is compact. You know this result or not? Every compact set is every set is compact even only if it is closed bounded. In
Yes, sir. Yes,
Rn,
yes, sir.
okay, it is not true in infinite dimension. So how do you show this part in the infinite dimension? You use what is called the Rees lemma. So this person F Rees, it's on the screen you can see. It's called a Rees lemma. Franco Rees, French person, and he proved this theorem in 1980. We are studying something which is more than a century old. Okay, but it is absolutely a fundamental concept in the whole of infinite dimensional. So this man Franco Rees is also called father of functional analysis. He developed the spectral theory also in functional analysis. Time getting at the end of the course, I will do that. Okay, provided your director and Nikhil accepts for me to do something which is not in syllabus. But definitely I won't ask you in the exam if I do that. Okay. So let X be a non-linear space. I will do this later. Okay. A very important result. That's why I want to do it there. What is the consequence of this? Let X be a non-linear space, Y be a subspace of X. Then you can have the quotient stuff here. That's what you have. Okay. Let me give you something more. This is on the quotient space. I will come and do it. The quotient space is a little bit. Let me see your syllabus here. Okay. This is the important theorem which I wanted to tell you. Let X be a non-linear space. Then the following are equivalent. What? Every closed bounded set is compact. The subset X, that is the closed unit ball, is compact. X is finite dimensional. All these things are equivalent. One implies the other, other implies the one. This is an important theorem, which is a departure from the finite dimensional space. This is obvious in finite dimensional spaces, but in infinite dimensional spaces, their life may be slightly difficult. This is called the closed bounded set is compact, Heine-Borel theorem. They are equivalent to the finite dimension. If the dimension is not finite, then it is not true. Such problems are called lack of compact problem. Okay. So that's the thing which I thought I will let you know on that. Okay. Let me see what else you do. Something about convexity. Convexity is good to do those who are doing optimization. Let me see your syllabus and try to do this. Okay. Okay. Now, it's a nonlinear space may have two norms. The norm and then the second norm you write it as norm prime. And associated metrics are dxy equal to norm of xy, d prime xy is norm of x minus y prime on this linear space. So if you have two norms, you have two matrices. The norm without a prime is said to be stronger. Okay. If the norm prime, okay, if the metric is stronger. What do you mean with metric is stronger? If something converges in one metric, then the other thing also converges in the other metric. That is what is called the standard. Comparable is that you can compare which one is smaller or which one is bigger. Okay. So let the two norms, norm and norm prime, be terms on a linear space. Then the norm is stronger than the norm prime if and only if there exists an alpha, such that norm of x prime is less than or equal to alpha times norm x for all x in x. This is whatever is said in the theorem is taken as the definition in many other books. Okay. That is why it says if and only. Okay. So the proof is simple, straightforward. Okay. What it says is when you take norm of x prime, it is less than or equal to alpha times norm x for all x in x. So you can compare the norm of x with respect to one prime norm, and then you can compare with the norm, the two-line norm. Okay. Further, something happens here. Not a very difficult story to do it. I don't know why he is complicating the life here, but we can do it in a simpler way. Okay. And this is a simple theorem. It's not at all a difficult theorem. This first part, norm and norm prime, they uses the topological definition. That something is stronger than this, then the ball of radius r is contained in the ball of radius one x prime. It's something. Something which is open in the one norm, prime norm, is also open in the other norm. That's what he is using. Okay. You can use this part here, and you can take 0 not x, and x is not a zero element, and you take epsilon greater than 0. Then you define, look at the norm of Rx over 1 plus epsilon into norm x. That will be bounded by R. Okay, that is how you have you use this inequality. Then it follows that Rx over 1 plus epsilon prime is less than 1. That is because of this inequality that is there. This is in the first norm without prime, and since it is less than R, it will be in this set, ball of radius norm x radius. So it is same thing as saying it is in the set norm of x prime less than 1. What does it mean? It simply means that norm of Rx over 1 plus epsilon norm x is bounded by 1. Push this norm x on this side. How can you push it? Because we have taken x to be not 0. Okay. So you get r times, so you push this here, you get r times norm of x prime less than or equal to 1 plus epsilon into norm x. Okay. And this is true for every epsilon greater than 0. So you let epsilon goes to 0 on the right side. You get norm x here. Okay. And you get here r of norm x prime. Push this r onto the other side and call 1 by r as alpha. Then you get norm of x prime. If you are pushing this r here, you get 1 by r into norm x. So call this 1 by r as alpha, then norm of x prime is actually alpha times norm. That tells you that if the two norms are equivalent, then this is true. Norm of x prime bounded by this. Other part is simple. Okay. This other part is simple because if xn is a sequence such that d of xn is going to 0, then xn minus x prime is also bounded by this because of whatever that alpha type is part. And therefore it will also go to 0. Therefore, the first one of them is a stronger norm. Okay. Now the example given here is the following, and this is the example which I wanted you to do it. In Kn means either Rn or Cn, you show that norm of x infinity is bounded by L2 norm of x2, bounded by L1 norm. Okay. And you also show that norm of x1 is less than or equal to root n times norm of x2 is less than or equal to n times norm of x3. That means the two norms x2, x1, x infinity are all equivalent. Okay. So if you wish, I will give a simple proof, but today it's already 55. Okay. And also the section is ending here. Okay. So I'll send this one to you. You read this material, which is not in the dancer's notes, and you try to note down all the doubts that you have in this part, and ask me, or you send a mail to me. I will answer the questions by mail, or I will answer the question when I am in Mizoram. Have a good day. Enjoy yourself.
Thank you, sir.
Bye. I am turning off the. I am leaving the call.
Thank you, sir.